And we'll go from current slide. And I'll just remind you of the two announcements I've been making all along. There are probably others, I just haven't found them yet. The college transfer fair days will be a week from Wednesday, that's February the 12th, from 9:30 to 11:30, Birmingham West Campus, B building, or academic building, B hall. Then 2 weeks from Thursday on this campus, in this building, in fact, February 13th, 9:30 to 11:30. They say campus cafeteria, I'm thinking in that area around the campus cafeteria, including faculty, staff dining room, and that kind of places, the hallways around there. That's where I'm guessing the tables will be set up. But there's lots of schools been invited. You certainly are encouraged and welcome to go by and talk with any of them. And then the internship that they're running this summer at University of Illinois, Arkansas, and Howard University, 10-week internship exposes undergraduate students to academic research in the fields of mechanical, electrical, and materials engineering. It's a fantastic sounding program. You're paid $5,000 to get all that experience, and you receive free housing, which I think includes free food, and airfare, one round-trip ticket as well. So deadline for that, they say on here is February 15th, which I wondered about because that's a Saturday, but in the brochure they say the 17th, which is a Monday, which makes a little more sense. All right, any questions on anything we've talked about or done so far? Anything? Okay. You can tell it's 70-degree weather out there. All my students have shorts and t-shirts on today, so that's February the 3rd. That's bizarre. At least it seems to me. All right, anyway. We were in Chapter 11, Vectors and Geometry of Space, 11.3, the dot product of two vectors, and that is leading to I think I told you before, the way it seemed like first learned the definition of a dot product, this was it. When the angle between two vectors is known, rewriting theorem 11.5, which we did last time, I'm pretty sure, in the form of the dot product of u dot v, is the magnitude of u times the magnitude of v times the cosine of the angle in between. That's the alternative form of the dot product. And that produces an alternative way to calculate the dot product. So it depends on what you know. If you know the two vectors and their components, just dot them and you got it done. But if you either need to know the angle or you know the angle and the dot product but don't know something about the magnitude of one of the vectors, is a variety of ways you can handle that. Let's see if they do example 3. No, they don't. So let's back up here and do example 3. Let me get my pen set up. Did I already ask any questions on anything so far? Okay. If this is what you know, the magnitude of some vector u, not necessarily a unit vector, in fact definitely not a unit vector, because its magnitude is 10. Okay? And you also know that there is a vector v whose magnitude is 7. And you happen to know that the angle between u and v is pi fourths. So I'm just going to say theta is equal to pi fourths. Now, just between you and me, that tells me something. going, let's see. Says find the dot product of U and V. So you don't know the components of U and V this time, so this way the second definition of dot product works. U dot V is equal to what? Magnitude of U times magnitude of V times the cosine of the angle in between. Okay? And in this case, that would be ten times 7. And what is that? Root 2 over 2. Okay? 2 will go into 10 5 times, and that will be 35 root 2. Okay, remember dot product is a scalar. That's as good a scalar as any, okay? If you want to figure out the approximate value of that, multiply it out. But that's how the book leaves it. 35 root 2. All right. Any questions on that? Okay. These are all the ones we did last time. And this time, now we move to direction cosines, which comes pretty much from that definition of a dot product. In space, it is convenient to measure the direction in terms of angles between the non-zero vector v and the 3 unit vectors I, j, and k. Okay? To measure the direction in space, now three-dimensional space, that's what I'll get started here. Convenient to measure the direction in terms of the angles between the non-zero vector v and the 3 unit vectors I, j, and k, as shown here. Okay? Now this is kind of hard to see because it's three-dimensional figure on a flat board, two-dimensional board. It's hard to see which direction this V is pointing. Here we have the I, J, and K unit vectors there. Okay? So this vector is either pointing out this way, appears to be fairly low angle with theta, but a pretty large angle with alpha, and a reasonable angle with gamma, on gamma, where alpha is the angle between the I and vector v, beta is the angle between j and vector v, and gamma is the angle between k and vector v. However, it's hard to say because of your perspective here. This could be anywhere in the first quadrant. It could actually be the second quadrant, or whatever the next, octant is over there. That vector could be pointing that way because that's a pretty good size angle going in here. So it's sort of hard to see where that vector is, okay? But that's how those are what we call, there. They show that the xy plane, there's the vector. Oh my goodness. Ryan decided to come today. Interesting, okay. All right, we're on page 773. Chapter 11, Vectors and Geometry of Space. 11.3 is dot products of two vectors. And we're talking about direction cosines. Okay. Now, this is in the first octant because there they indicated where your vector v maps onto the xy plane. So it is in the first octant. The I component is positive, not very large positive. J component is fairly large positive, and they don't say too, that would be your K component here, which is in between those two. Okay. So those are your, what they call your direction angles. And this leads itself to the angles alpha, beta, and gamma are the direction angles of that vector v. And cosine alpha, cosine beta, and cosine gamma are the direction cosines of that vector v. Now, because this vector v, which is coming up in the first octave here, dotted with the x component there, I, would be, by our second definition, magnitude of v times magnitude of I, which we know that is. What is that? Magnitude of I. Say again?
Positive.
Yes. Magnitudes are always positive. Good guess. Okay. One. It's a unit vector. Okay, they didn't put the hat on it, but the ijk components are unit vectors. Okay. Times the cosine of the alpha. Okay, and because the magnitude of I is 1, it can just be magnitude of the vector v times cosine alpha. That's the dot product between v and alpha. Now, the other way to do it is v is v1, v2, v3, whatever the components are up here in the first octave, which were not quite shown in this figure, but could be, well, they sort of were. Here's the I component would be the distance from the y-axis to here. The j component would be the distance from the x-axis to there. And the k component would be this length right here, because that maps over here. So they kind of were shown there, but not exactly. Okay? But it does have 3 components, because it's in space, vi, v2, v3. Well, that dotted with the I vector, which is what this is, 1, 0, 0, that would just give you v1. Oh, wait a minute, okay? The dot product of v with I is v1, and that is magnitude of v times the cosine of alpha. Well, what is cosine alpha would then be the first component divided by the magnitude of the whole vector. Okay? Magnitude of the entire vector v. Now, this magnitude, you know, has to be less than v1, not because the square root of v1 squared equals v2 squared equals v3 squared equals v the square root of that. So, only if these were in, if vector v was along the x-axis, would they be the same, that it would be 1, then the cosine alpha would be 1, alpha would be 0 degrees, and that would be if they were along the same axis. Yeah. Okay, so this means this is greater than that, which makes sense because cosine has to be between -1 and 1. Now they showed this being first octave, so this would be positive in that case, but it could be in some other octave and have a negative cosine, because v1 doesn't have to be positive. All right. Does that kind of make sense? You might say, so what? Okay, where are we heading here? But similar reasoning, though, unit vectors j and k, you would then have cosine alpha is equal to v1 over magnitude of v, cosine beta is v2 over magnitude of v, and v3 and cosine gamma would be v3 over cosine v. Over magnitude of v. So alpha is the angle between v and I, vector v and the unit vector I. Beta is the angle between vector v and j, unit vector j, and gamma is the angle between vector v and unit vector k. Okay, here are these 3 representations. Consequently, any non-zero vector v in space has a normalized form of when you take vector v, divide by its magnitude, what you have is a unit vector in the direction of the vector v. Now, they didn't say that here, but we know that's the case. They say it down here. And this would be the vi over magnitude v, v2 over magnitude v, I, j, and k here. This is simply cosine alpha I cosine plus cosine beta j plus cosine gamma k. And because that's a unit vector, it follows that the square root of this squared plus that squared is equal to 1 squared, which the square root of 1 squared over 1, which means that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. Okay? So again, you may say, so what? Okay? Yeah, we've got this. It's pretty interesting stuff, but so what? Okay? Well, I don't know. We're just going to move on to do example 4. Find the direction, cosines, and the angles for the vector V is equal to 2i plus 3j plus 4k. And show that cosine squared alpha plus cosine squared beta plus cosine squared gamma is indeed equal to 1. So first, find the direction cosine. That would be cosine alpha. What's cosine alpha? Oops, it was right there. This is that. Oh, where did it go? Oh, I'm going the wrong direction. No wonder I couldn't find it. There we go. It's what? 2 over what? Don't think so. Say again? Okay, let me see if that's right. Looks more like 29. Isn't it? Yeah or nay? Okay. So 2 over root 29. Huh. Get 9 in there. What would be cosine beta? Three over root 29, and cosine gamma, 4 over root 29, if I could write. And then the question is this true? Cosine squared alpha, which would be 4 over 29 plus 3 over 29 plus 4 over 29. Is that equal to 1? If I had squared them, it would have made sense. That's 6. I squared the first one, but I didn't square the next two. Sorry. Okay. 4 over 29 plus 9 over 29 plus 16 over 29. Sure enough, that's exactly how we got our 29. Adding 16 and 4 is 20 and 9 is 29. That is indeed equal to 1. Okay. Now, I didn't read the problem well. It said find the direction cosines and angles. I didn't see the and angles part. So we need to actually calculate and see what the angle alpha is. How do we do that? Okay, doing an inverse cosine, right? Okay, so inverse cosine of 2 over root 29.
This is the green one, right?
They're putting it in degrees. You could do either, but they put it in degrees. Oh, I I can't say root 29 without thinking of something.
So alpha is 68.2.
68.2 degrees. Beta would be?
56.1.
Beta would be approximately 56.1, you said?
Yes.
Yep.
And 42.0.
And that's what they got. Good for them. Okay, now, I went to Georgia Tech. I think y'all probably have heard that. And if you think, well, football-wise, I would say probably the rivalry between Georgia and Georgia Tech is strong. Probably not quite as much as Alabama-Auburn, but it's pretty close. But then there's also just the rivalry between the schools, and maybe that's there with Auburn, Alabama as well. But a friend of mine did go to University of Georgia, but his uncle, I think it was, went to Georgia Tech. And one of the two major highways that connects Athens, Georgia with Atlanta, Georgia is Highway 29. And his uncle said the only good thing to come out of Athens is Route 29. So I can't think of Route 29 without thinking of that story. But that's beside the point here. That's, if I can find, yeah, that we just finished example 4. We did it, 2/3 of it. I forgot, I didn't find the angles. But let me, since you just came in, I'll let you see how they did it without having to read my ugly writing. So here's the first part, because the magnitude of V is, so that's the first thing you've got to do, your direction cosines, cosine alpha, alpha being the angle between the vector here and the unit vector here. Okay? That, between the first unit vector, I, that will, by definition, is the component of V in the I direction divided by the magnitude of V. So the first thing you've got to do is figure the magnitude of V, which is the square root of 2 squared plus 3 squared plus 4 squared, which is square root of 4 plus 9 plus 16, which is the square root of 29. That's root 29. So once you have that, you can write down what cosine alpha is. It's the magnitude of the I component 2 divided by the I component divided by the magnitude of the vector 2 over root 29. And that would then yield you alpha being about 68.2 degrees, taking inverse cosine of it and degreed mode. Cosine beta would then be 3 over root 29, which would then be, now I'm so used to thinking in terms of sines, it just seems bizarre that with the smaller number, the angle's going up. But cosines, they go that way. And so beta would be about 56.1 degrees, and cosine gamma would be 4 over root 29, which would be yield to gamma being about 42 degrees. Now, show that the squares, sum of the squares of those three angles is equal to 1. Well, you just square 2 over root 29, add to that the square of 3 over root 29, add to that the square of 4 over root 29. It would be 4 over 29 plus 9 over 29 plus 16 over 29, and again 16 plus 4 is 20 plus 9 is 29 over 29 is indeed 1. So it is, the sum of those is 1. All right. Any questions on that? Let's see if that's what we've got here. Oh, no. A different perspective could be the same vector you saw earlier. could be the 2, 3, and 4. That looks fairly reasonable. It doesn't, to me, look like the gamma in the earlier one was quite as large. So anyway. Oh, here's the picture. Alpha is this angle between the x-axis and the vector v. Beta between the y-axis and vector v. Gamma, the z-axis, and vector v. This alpha being greater, which it does look like it could be, that one a little bit less, than the smallest of those three. All right. Any questions? Now, let's move on to projections and vector components. Those of you who have already had your physics, this is going to be, I hope, some old hat to you, okay? Those who haven't, this may be a little on the new side, but it should be pretty easy to follow. You've already seen applications in which two vectors are added to produce a resultant vector. Many applications in physics and engineering pose the reverse problem, decomposing a vector into the sum of two vector components. Okay? In other words, you have a sum, and you need to know its components that make up. The following physical example enables you to see the usefulness of this procedure. Sort of a classic type problem in physics. Consider a boat on an inclined ramp, as shown here in this figure. The ramp has an angle. I don't give you the angles, is it? Interesting. Usually they do. Okay. As shown here. The force F that you're having to either pull to get the boat out of it or resist to keep it from rolling back into it. Force F, wait, I'm sorry, and I talked about that before. The force F due to gravity, which is the one down here, which usually I call weight, okay, pulls the boat down the ramp and against the ramp. Now what they mean by that, gravity always points straight toward the center of the earth, okay? If you break that vector there into two components, one parallel to the ramp, the other perpendicular to the ramp, this is the component they're saying is pulling it down the ramp, W1, and W2 is pulling it into the ramp. Gravity is pulling the boat into the ramp. Now that's a weird way to express it, but it is indeed what, or against the ramp, they call it. Those two forces, W1 and W2, are orthogonal to each other, and they're called vector components of the vector F. Okay. Now, what?
Could you explain what orthogonal means?
The what?
Could you explain what orthogonal means?
Orthogonal, perpendicular. At right angles to. Okay. And here's at least a quick and dirty of the physics of this. Okay. Generally, what we're looking for is the force. That's what I was starting to say. The force that you're having to pull against the boat to keep it from going into the water, or against the boat to pull it out of the water. That's the force you're usually interested in. Okay? Now, the only force you're acting against is the force due to gravity, weight, down. This force has to equal the component parallel to the ramp, or they call it the ramp. This component is called the normal component. Normal meaning perpendicular to the surface, okay? And so the ramp is pushing up on the boat with a force equal to the boat pushing against the ramp, okay? So the normal force would be perpendicular to this force. I mean, it's parallel to this force in the opposite direction. and equal, absolutely equal. So the only force that you're having to pull is against this one, not against the weight necessarily. The ramp is supporting most of the weight. You're just pulling against this one here. Okay. Now, I don't know if they're going to get into this now, but here's what I would suggest to you. Think of this also as, of course, a perpendicular angle. It's the same one as that one. Okay? And just for funsies, also think of the angle here of the ramp with the horizontal. Okay? Now, if you think of that, you can see that this angle here is equal to that angle because this is a common side here. This is horizontal here. That's horizontal there. There's a transect that cuts those two horizontal parallel lines. Its alternate interior angles are equal. Okay? Now, and of course, this angle is also 90 degrees. So you have a second angle here, which is complementary to this one because those add to be 90 degrees. Because this is a 90-degree angle, and this is a 90-degree angle, and this angle is common to both. That means that vector length is common to both. If we extended that on up to it really doesn't matter which way you do it. Extend that up to here and have this angle being, this W1 being here. That would be the same thing. It's just same angle. Then you see that W1 makes an angle here equal this is getting really crowded here. What it gets down to is this angle here is the same as that angle there. So if you know the angle of the boat ramp, you can deduce a whole lot of this information and actually calculate it. Let's see what the problem is, okay? So we see here that the force due to weight, F downward, is equal to the weight parallel to the boat ramp plus the weight perpendicular to the boat ramp. That's what this statement says. Vector components of W parallel to the ramp, perpendicular to the ramp. Forces W1 and W2, notice those are vectors also, help you analyze the effect of gravity on the boat. Yeah, F is the effect of gravity on the boat. For example, W1 indicates the force necessary to keep the boat from rolling down the ramp, that's what I said before, whereas W2 indicates the force that the tires must withstand holding against it. In other words, the normal force, perpendicular to the ramp. Okay? Not that you're usually interested in W2 that much, it's W1 that's usually a greater interest. So here's, without doing anything else with that problem, except just introducing it, here's the definition of projection and vector components. Let U and V be non-zero vectors. We don't mess with zero vectors unless we absolutely have to. Okay? Moreover, let U be split into two components, W1 and W2, similar to what we did before, where W1 is parallel to V and W2 is orthogonal or perpendicular to or at right angles with V. Okay? So one is W1 is in the direction of V, W2 is perpendicular to V, as shown here. So here's your U here, your V here, and U is split into one component, W1, in the direction of V, and the other component, W2, perpendicular to V. Okay. Now, W1 is called the projection of U onto V. Even though V doesn't extend out that far, that would be the projection of U onto V. Or the vector component of U along V, or in the direction of V. And is denoted as W1, this one down here, that is a vector, is equal to projection of U onto V. Okay? Projection of U onto vector V. W2 is then U minus W1, okay? Because that's the difference. The sum of these two is U, so the difference of U in this one is W2. That's called the vector component of U orthogonal to V. We don't have a shorthand for that. It's just the other side of that. Now this is if theta is an acute angle. If theta was obtuse, then again, W1 and W2 are your vector components of the vector U. W1 plus W2 is equal to U. But the projection of U in the direction of V would then be a minus there, which indicates, since this is second quadrant, indicates probably has to do with the cosine, which would be exactly right, because the cosine would be the negative. So here's vector V. This is still projection of U onto V, even though it's in the opposite direction. Okay? And then this would be the projection, the component of U perpendicular to V. W1 is projection of U onto V. Projection of U onto V is the vector component of U along V. W2 is the vector component of U orthogonal to V. W2 in both cases. Losing my voice. Example 5. Let's do it. Find the vector component of U is a vector 5, 10, that is orthogonal to V, which is the vector 4, 3. Okay? Why did they give you all this? Why didn't they just say do it? Okay? Oh, maybe they haven't shown you how to do it yet. Okay. All right, W1 is projection of U onto V. And how did we do that? Oh, they told you that. It's 8, 6. Okay? Now, without telling you how they got that, notice it makes you feel warm and fuzzy. It's obviously in the same direction as V, right? Projection of U onto V is in the same direction. Longer than V, in fact, exactly twice as long as V, but it's that projection, okay? And then U, of course, is 5, 10, and that is W1 plus W2. So they've made it pretty easy to get W2, right? Find the vector component that is orthogonal to V. That would be, this is parallel to V, this is perpendicular to V, okay? I threw that in, but you don't have to do it that way if you don't want to. So then W2 is equal to U minus W1, okay? Which would be U is 510 minus W1, which is 8,6. And that would be what? Second, negative 3,
4.
4. Ding, ding, ding. Correct.
That's all it is?
That's all there is. Sorry. They did most of the work for you there. But don't worry. In the future, you're going to need to determine what W1 is and therefore do the rest of it. Here they gave it to you. But we'll soon see how to do it. Now, is this indeed perpendicular to V? How can you tell? How can you check orthogonality, perpendicularity, or whatever the word would be? What's true about? Second?
They intersect.
Okay, they do intersect. Whether they're like this, they don't intersect, but they still could be perpendicular to each other. What's true about one of the operations that we happen to be dealing with in this section, and perpendicularity, or whatever you would say, orthogonality is much easier. What is the topic of this section? The dot product. What does the dot product of two perpendicular vectors have to do? Always. Ooh, important thing to remember about dot products. Let's see if we can find that quickly. Yes, the dot product is 0 of two perpendicular vectors. So let's see if indeed that's the case here. What's the dot product of U and V? I mean V and W2. Negative 12. Plus 12 is 0. Right? These two had better be perpendicular to each other. Let's see if that is indeed the case. Where's our W? There's our W1, and here's our W2. That would be 24 minus 24. Plus 24 is 0. Yes, yes, yes. Okay. Now, they made that really simple, didn't they? Okay. Let's also throw in the graph, which I'm glad they've drawn, and I don't have to. So let's do that part, because U is W1 plus W2, which we see right above us there, where W1 is parallel to V, which they told us it was, and it is, and W2 is the vector component orthogonal to V. All you have to do is W2 is U minus W1, which is 510 minus 86, which came out exactly negative 34. To check to see that W2 is orthogonal to V, they show the picture. That doesn't tell you anything really. I can't tell for certain just looking at this, those two are perpendicular. But I can do a dot product of this one and that one and tell you exactly that's equal to 0. Okay? But here's how they look. Here is the component W1 in the direction of V. And sure enough, we knew that's the case because 4, 3, 8, 6, this is exactly twice that, so it has to have the same direction. It's scaled up by a factor of 2. And then when you subtract that, this had better come out perpendicular to that, because that's how we define it. But you can check it easily by either doing this dot product or that dot product. Both of them get 0. So, how do we find that projection? Using the dot product. So if U and V are any two non-zero vectors, then the projection of u onto v, so projection of u onto v is equal to the dot product of u and v divided by the magnitude of v squared times the vector v. Okay, now, may not be intuitively obvious, they're just telling you that is, and it is indeed true. But if you think about it sort of this way, and this is really a gross way to do it, but it kind of is. If you think of this as this over one of these, that's a unit vector. This over the other one of these, that's a unit vector. That would give you u, and that sure enough is what you get. So this is u projected on the v. That leaves something to be desired, but anyway, that's how I have to remind myself what that is. The projection of u onto v can be written as a scalar multiple of a unit vector in the direction of v. That's what we saw before. It was twice. It doesn't have to be a nice round number 2 like that. It can be anything. But this would be, and this is sort of what I just did, pull out one of these under here. That's a unit vector. Okay? This is some scalar quantity, and that scalar quantity is multiplied by the unit vector in the direction of v. Okay? Now, if you also think back, not that far, yuck. Maybe it is that far. Yeah, okay. Seemed like we hit it. Okay, I'm going backwards. You don't see all the things. U dot V divided by magnitude of V. Remember, that was what we had here. That would give you U, magnitude of U times the cosine of the angle in between. We're getting close. Well, I'll forget it before we get there. Okay. So what we have here, the dot product divided by this is indeed the magnitude of u times the cosine of the angle in between. That's what this k is. This is that, and it's this. So that is a scalar value times the unit vector in the direction of v. Scalar k is called the component of u in the direction of v. Component of u in the direction of v. But again, that kind of looks like what we've got here. V over magnitude of v is the unit vector in the direction of v, and this would be the component of that in that direction. That scalar k would be that. Okay. So let's see if we can put those together. Find the projection of u onto v and the vector component of u orthogonal to v for u is 3i minus 5j plus 2k, v is 7i plus j minus 2k. So I guess what we want first is projection of u in direction onto v. Okay, and what was that formula we just were playing with? U dot v over, okay, that's it. Okay, okay, times times the vector v, exactly. Okay, okay, so that will be the projection of u onto v. Okay, so what do you suggest we do first? Several things you got to do. What you want to do first? Okay, let's do it. U dot V. What's that equal to? Second?
It went away for a second.
Oh, it did? Oh, okay. It came back. Okay. What would that be? Not that hard, is it? You don't have to do it all. Just give me the pieces. U dot V. 21 minus what? 5 minus 4. Okay. And that would be 21 minus 9 would be 12, is it? Okay. My day's been going like that too. Okay. Okay, there's U dot V. What's another part we've got to do? Okay, squared. And what's the shortcut for that? Do you remember that one? Don't remember that? V dot V. I'm going to do it in the book. That's easier to do than doing this. If you go back to page 770, number 5, V dot V is magnitude of V squared, number 5, theorem 11.4. Okay? So that's going to be pretty easy to do, I think. What would that be? Quickly. Fairly easily. Okay, 49 plus 1 plus 4, which would be 54. Okay, don't have to take square roots or anything. That gives it to you right there. Okay, so what is this quotient then? U dot V over magnitude of V squared.
So we've got 12 over 54.
12 over 54. Can we reduce that any? 2 over what? Like 3?
He said 9.
Huh? 9. 2 over 9? Okay. Yeah, 6 will go in 2 over 9. Right. 2 ninths. Okay. So that would be 2 ninths times vector V, which is 7. I like component notation best. 1, negative 2. And this will be 14 ninths, comma, 2 ninths, comma, negative 4 ninths. Okay, so there's a projection of U onto V in the same direction of V. Okay? We know it is because we multiplied the scalar times that vector. Okay. Now, that was the first part. Find the projection of U onto V and the vector component of U orthogonal to V. Now, how are we going to do that? What would be the... Okay, this would be, I can't remember, which we call W1 and W2. Was W1 in the direction or, yeah, in W2, that's what we're looking for. Okay, W2 is what we're looking for, and that would be what? U minus W1. Now that's not too bad, is it? So U would be, tell me what U would be in component notation.
3 negative 5.
2 minus what we just got, 14/9. 2/9. I love fractions, don't you? Negative 4/9. Now, to make that a little easier, not much, but a little bit, let's write this one in ninths. How many ninths is 3? Anybody? How many ninths is 3? No. How many ninths is 3? Okay. I have 3 pieces. Yes, 27/9, isn't it? And how many ninths is negative 5? Negative 45/9, right? How many ninths is 2? 18/9. Okay. And subtract from that, whoops, left off my subtraction sign, 15/9. I think that's, if I can read my writing. No, that's 14/9. Yeah, that's a 14/9, isn't it? Who writes so sloppily, huh? I can see it now, but goodness gracious. 2/9 minus 4/9. Okay, so what would that W2 be? That's what you get for your taxes, isn't it? Anybody? 27 minus 14? Not that hard, is it? 13/9, comma. Got it? 22/9. Okay. There we think is W2. Okay? Let's see if we can. I have lost my. Oh, did I? I must have turned back. No, I didn't. Where is this? There it is. 13/9, negative 47/9, 22/9. Yes. Okay. So I think we've done both parts. We found the projection of U onto V, and that was that part. And then we found the projection of the vector component of U orthogonal to V. So let's clear the screen. Any questions before I clear it? Everybody got it? Okay. Now let's see how they did it. The projection of U onto V is W1, which is U dot V over magnitude of V squared in the direction of V, because this is in the direction of V. I wish they'd have made that a bolder V, but it's subscript, so it's hard to see. But that is a vector V, okay? And lo and behold, they came out with 12/54, which they left it that way. Shame on them. And that's multiplied by V, which is that. And they reduced it finally and got 14I plus 14/9 I plus 2/9 J minus 4/9 K. Another way to express that is 1/9 of 14I plus 2J minus 4K. But that makes it a little confusing. And then the vector component of U orthogonal to V would then be the difference between your original U and W1, which you just found, which would be exactly that, but that's an awkward way to express it. But they didn't bother them any. They just wrote down the answer without telling you how they got it. But that's exactly what we got. Right? Any questions? Okay. So here's the figure. Thank you for drawing it so I didn't have to. Okay. I'm still not sure it clears up very much. Here was the initial vector u, which we know was that. Now here, the orientation is x, y, z. Positive x, positive y, and z up. So 3I, that would be somewhere about right there. Okay, because it's 2, 4, 6. So it would be somewhere right in there in the I direction. Minus 5j, and this would be 2, 4, 6, so that would be here. Sure enough, that doesn't quite look right, but it's close, okay? Plus 2k, so this would be 2k, that looks about right, okay? Drawing three-dimensionally on a flat thing is hard to see. Putting these little things in helps a little bit. Okay. Now, subtract from that, well, first, to get the component of this, well, here's vector v over here, which they don't show on the screen right now. Let me see. We've got it anywhere close to right. 7I plus j minus 2k. Okay. 7I, that looks about right. What did I say?
It's right there.
Plus 2I, j?
The vector's on the graph.
Plus j. Huh? Second?
The vector's on the graph.
Yeah, I see it here, but I'm just seeing plus 7 plus 1, j. So yeah, that's about right there. And then down 1, or down what? 2k, wasn't it? And that looks about right there. Yeah. So there's the vector. Now, projection of this onto that is going to be a pretty short vector here, because these are getting, they're not orthogonal, but they're getting fairly close to it. So that gives you a pretty short vector there, and that's exactly what we've got here. This is kind of small. They lost part of the 9 there for some reason. So here's your vector W, which is 14/9, which is less than 2I. That looks about right. And 2/9 J, not very far out here at all. And minus 4/9 K, so not very far down here. So that would be your W1. And then the difference between this one and that one, of course, would be that one, which gives you something closer to this. They don't show you where this is there. 13/9 I, which is less than 3. It's so hard to see the projection there, but indeed that's what you got. Okay. Yeah, you can see the figure, but it almost drives you crazy trying to follow it. Now, they skip example 7. You know, you almost expected they would, okay? Let's see if we can do example 7 here. How are we doing on time? Plenty of time, right? 30 minutes. Okay, I thought so. Okay. Here we have a 600-pound boat sitting on a ramp inclined at 30 degrees. That's the ramp. Okay? Now what I think I'm going to do actually is go back to this picture, and let's use this picture. Okay? So a 600-pound boat, that's your F. That's the weight of the boat, 600 pounds. By the way, those of you who haven't had physics yet, pound is a force. Okay? So that's a good unit for that. 600-pound boat sits on a ramp inclined at 30 degrees. Now they haven't, I'm not sure this picture is very good, but we're going to say that's 30 degrees. Okay? Maybe a little short of that. It is a little short of that, but let's just call it 30 degrees. Okay, as shown in this figure, kinda. What force is required to keep the boat from rolling down the ramp? So what force do you need here? Let's call this F retarding force that you have to keep the boat from rolling down the ramp. Okay? Now, this is the figure that shows this best. We know that's 30 degrees. We know this is 90 degrees. You know this one's got to be 60 degrees in this case. Okay? But you also know that that W1 and W2 are 90 degrees, and if this one here is 60, that means this has to be 30 degrees here too. So that's why I said that those two angles do have to be equal. Okay? And this one, of course, would be 60. Okay? Which means this one would be 30. Okay? That's 60. There's 90. I mean, you can put them in there anywhere you want to. Be sure you put them correctly. Okay. So, as I said before, the retarding force here is only W1. Okay? That's it. Okay? Now, there's no reason to do anything else but use our, and we did do our components in terms of sines and cosines, right? But even if we didn't, we can do them here. Okay? Right? So if this angle here is 30 down here, what is this? And this F is 600. What is W1? That's what we're looking for. If we know W1, we know F sub R. It's just in the opposite direction of that. Okay? So, say that again now. Okay, the theta can be anywhere you want it to be. I just assume that be our theta, because that's what they gave us here. Right? So 30 degrees. And here's your right angle here. Okay, sine of 30 degrees W1 would be the opposite over 600. Agreed? So what is W1? Solve for W1. Help me. 600 times sine of 30. But we know that one, don't we? That's one of our favorites. 300 pounds. That's the force that this has to exert to keep it from rolling down the slope. I can't write, but £300, because whatever the weight is there, that's what your retarding force has to be to keep it from going. So 300 pounds required to keep the boat from rolling down the thing. Now, they did it in terms of projections, which I'm sure is a very nice way to do it. But why? I mean, if you draw your pictures, label your things, you see it's got to be that. Okay? So, anyway, a lot easier than doing the other way, I think. All right. Let's move on to, any questions on that before we leave it? I'm sorry, did I leave it too soon? Any questions? Everybody got it? Okay, it's about time we get to work in this course, okay? The work done by a constant force W acting along the line of an object, that means along the line of motion of an object, is given by W is equal to the magnitude of the force times the displacement, okay? That is if the work done by a constant force acting along the line of an object, given it's in the same direction of your displacement. So it's just the magnitude of F times your displacement PQ. That is if the force is along the line of the object, in other words, in the same direction the object is moving. That's what it is. I'll give you a little clue here. That is an italicized, regular case, not boldface thing. This work is a scalar quantity, not a vector quantity. Okay? Because you got a magnitude here, magnitude there. Product of that is going to be a magnitude. Okay? That's your basic definition of work. Now, that leads to, what if the force were up here? Or, in some other thing. I can easily see you pulling this way rather than straight this way, especially if something really low to the ground. I want to pull like this. I don't want to stoop way over there and pull. I'm just lazy that way and my knee hurts, okay? So, what happens if the constant force is not directed along the line of motion? Like here, you're pulling at an angle. Well, then the only component of that force that is doing work is the component along the line of motion. So then, that's the projection of F along PQ. Okay? So W is equal to the projection of F in the direction of PQ times the magnitude of PQ. This is the magnitude of this component of the force. Well, this is the cosine of theta times the magnitude of the force, okay? Yeah, okay, because if there's the force, there's the angle theta, then the projection, the force in this direction is this component, which is cosine theta is adjacent over hypotenuse. So the adjacent would be the hypotenuse times the cosine theta. So that gives you this component times that. And there. And what is that? That is the force dotted with the displacement. Oh wow, there's a fantastic example of a dot product right there. Now, remember, a dot product produces a scalar answer. Work is a scalar quantity. Okay. So work x at an angle theta with the line of motion, okay, in this case. Force x, okay. Now, catch this. This component of the force, the upper component, does absolutely no work on this body. None. Until you get into friction, okay? Because friction depends on normal force. If you have friction here, that's equal to the coefficient of kinetic or static friction times the normal force. Well, this component of force reduces that normal force. Because the weight's still the same. If you have a component here and a component here, this reduces that component from what it would be. So it does help in many ways. Pulling down this way actually hurts because that increases the normal force beyond what just the weight would be. So this notion of work is summarized in this definition. Definition of work. The work W done by a constant force F at its point of application, moves along the vector, as its point of application, moves along the vector PQ, that's your displacement vector, is one of the following. Either work is the projection of F in the direction of PQ, projection of F in the direction of PQ, times the magnitude of PQ, or just simply force dot PQ. I like that one better, okay? That's so much simpler, more direct, and if you know those pieces, you got it. If you don't know the pieces, maybe the other part will work. But basically, you got to know these pieces to make that part work. So that's the dot product form, or the projection form, either one. Though, here we have the figure at the bottom of page, example 8. To close a sliding door, a person pulls a rope with a constant force of 50 pounds at a constant angle of 60 degrees. Okay? I think they showed everything there, except they didn't show that capital F, the force is 50 pounds. So I'll try to kind of write that in here. This is 50 pounds. That's the magnitude of that. Okay? At a constant angle of 60 degrees. So there's your angle, 60 degrees, as shown in this figure. Find the work done in moving the door 12 feet to its closed position. Okay, that's kind of a weird perspective they have on it, but I guess it's okay. I would have drawn that straight out from that, but okay, 12 feet. Showing how far the guy is pulling it. Okay. Now, I'm sure they're going to do it by projection. Okay? So I guess we need to put up with it. I mean, do it that way. Okay. What would be your projection then? The projection of PQ, F in the direction of PQ. Okay, going back to this formula here, this is what we're looking for first. The projection of F in the direction of PQ. So let's do that first. This thing right here. Anyone want to hazard a guess what that is? Say again?
So F is 50.
Okay, F is 50 pounds. You want to write that down? Okay, we'll do that. That's magnitude of F. Okay. Now remember, PQ is a displacement vector. So it's not measured in pounds, it's measured in feet. Okay, so that would be, now I keep trying to hear the definition for projection. I got magnitude of F, magnitude of PQ. What else do we need? There we have it, huh? Well, no, okay. If we're choosing to do it this way, using this formula, then the projection of PQ on F is this. Right? Okay. We got magnitude of PQ. Yes. Yes, yes. Whoa, I'm going the wrong way again. Yeah, I'm sorry. Okay. Times the cosine of the angle in between, and sure enough, that is 60 degrees. Okay, so that would be 50 pounds, magnitude of F, times magnitude of PQ, 12 feet. And what in the world is the cosine of 60 degrees? That's supposed to be a 1 degree, not another 66. 6.
60 degrees. 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 60 degrees
Second? 1/2 again. Okay, so let's just do this one into that one and make it 6. And 6 times 50 is 300 what? Foot-pounds. 300 foot-pounds of work. That is the work that was done. Okay. Notice work is usually, I think I said this last time, capital W, because quite often weight is little w. Okay, they're not using that necessarily in this book that much, but it is the case. Weight, however, it's a vector quantity. Work is a scalar quantity. And let's see, make sure they got it right in the book. Yes, they did. Good for them. That's how much work the farmer did there. Okay. Notice his pulling down. Now, this is assuming no friction. Okay. Lucky barn door there. Okay. But he still has to pull with that. Okay. So, using a projection, you can calculate the work as follows. W is equal to projection of on F in the direction of PQ times the magnitude of PQ, cosine 60 times magnitude of L times magnitude of PQ. But they gave us those 1/2 of 50 times 12, which is 300 foot-pounds. Now, have any of you ever used a wrench that was scaled in foot-pounds? No. If you ever run into one, that's called a torque wrench. Is torque the same as work? No, it isn't. Okay? Torque is the cross product, we haven't gotten there yet, of force times displacement. Okay? Only it's a different displacement there and sort of a different force as well. That's a perpendicular type of multiplication of vectors, not parallel. Okay? These would be maximum when it was perpendicular. And it's also a vector quantity, not a scalar quantity. And we'll see that coming up in the next section. So anyway, let's, homework exercises here include any of the odds, 3 through 9. They're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 17, they're all at Calc Chat. 13's at Calc View. Do number 19, it's at Calc Chat and Calc View. Any of the odds 21 to 25, all at Calc Chat. 27 or 29, both at Calc Chat. 31 to 35, all at Calc Chat. 31's at Calc View. 37 to 43, all at Calc Chat. 37's at Calc View. You can explore doing 45 and or 47 if you choose. They should have the correct answers at Calc Chat. If they don't, you don't need to worry with it. Then 49 should be at Calc Chat. 51 and or 53 should both be at Calc Chat. And then a bunch of problems. You can do any of the odds 55 through 61. They should all be at Calc Chat. There's true false 63 should be at Calc Chat. 65 and or 67 should be at Calc Chat. And then come some proofs. Any of the odds, and then there's a bond angle stuck in the middle of these. 69 through 75, they should all be at Calc Chat. Now, looking at some of those, though you may not choose to do it, there's one called the Cauchy-Schwarz inequality. I think we ran into that in the text. If we didn't, we should have. Also sometimes called the triangle inequality. And the reason I even bring it up here is you can choose to write about Cauchy and or Schwarz and or how they came up with this and or how we use it. There's several potential topics right there. Any questions? All right. I keep bringing up the idea of the papers for a reason. This, of course, one of my best classes of all time. How many papers we got in after nearly a month of class? 0. Okay, so please be working on your papers. What's that? I can't hear you. Oh, okay. How many do I have? 0. Okay. So sort of make an exchange here. Okay. Now, any questions on 11.3? That certainly kept us going long enough, didn't it? Okay, let's move on to 11.4. And it'll take a while for PowerPoint to do anything. Here we go. Not as long as I had feared. We'll go from current slide. So we're still in Chapter 11, Vectors and Geometry of Space. And 11.4, the one I was just referring to, the cross product of two vectors in space. So we'll first find the cross product of two vectors in space. We're not even messing with planar yet. And then we'll use the triple scalar product of three vectors in space. So let's first look at what in the world the cross product is. That is pretty interesting. Way back in when you were first learning multiplication, I bet you used the time signal that was like a cross, didn't you? But then when you started getting into algebra and your favorite variable of all time was x, and that looked a lot like the cross, it became not the best thing to use for multiplication. So we went then to the dot to represent that. Well, vectors, since they have two types, in some senses, of multiplication, they went back to the same symbols. The dot product was when you produce a scalar answer. The cross product is when you produce a vector answer. They're both multiplications, but different kinds of multiplications. Many applications in physics, engineering, and geometry involve finding a vector in space that is orthogonal or perpendicular to two other given vectors. So let's say you have a vector here and then another vector here, okay? Now, to find the vector that's perpendicular to those two, it would have to be this way, right? That's going to be another vector. It's not going to be a scalar, okay? Now, these two could have been crossed like this, in any way, but the perpendicular vector will be that. So in this section, you'll study a product that will yield such a vector. It is called the cross product. It's the most conveniently defined and calculated using the standard unit vector form. Okay? That's true. Because the cross product yields a vector, it's also called the vector product. Now, calling it that does have a little bit of a disadvantage, because then you're tempted to call the dot product, because its answer is a scalar, the scalar product. And it has been called that, except that we usually use the term scalar product to mean multiplying a scalar times a vector, okay? Not a vector times a vector getting a scalar. So there are some issues there. Okay. Now here's a definition of the cross product of two vectors in space. Here's one vector, u. It's u1i plus u2j plus u3k. This is the standard unit vector form, or something like that. Vector v would then be v1i plus v2j plus v3k. Those are both vectors in space, meaning three-dimensional space. The cross product of u and v is the vector u cross v, that is a vector, not a scalar. And lo and behold, it's u2 v3 minus u3 v2 I minus u1 v2, no, v3 minus, this is in parentheses, minus u3 v1 j plus u1 v2 minus u2 v1 k. Yeah, you're going to memorize that, aren't you? Now, immediate note, please don't. It is important to notice that this definition applies only to three-dimensional vectors. Now, that's not saying you can't do cross products in bigger dimensions, but let's not if we can help it. But cross products pertain primarily to three-dimensional vectors. Okay? And certainly this definition only applies to three-dimensional vectors. Now, that's the writing down of it. Here's the easy way to do it. Convenient way to cross two three-dimensional vectors, okay, is to use a determinant form with cofactor expansion as shown here. And to me, this isn't the easy way. It may be a convenient way. This isn't the easy way. I'll show you the easy way in a minute, okay? But here is the determinant form with cofactor expansion shown below. Okay. U cross V will write in the determinant. Determinants have to be square. The top row is going to be IJK, your unit vectors. And your next row is going to be the components of those components of the first, U1, U2, U3, and the third row is the components of the second vector, V1, V2, V3. Okay? Put the components of U in row 2, components of V in row 3, and your standard unit vectors as your top row. Now, to get the I component, here's what determinants do. You wipe out the row that comes in and the column that comes in, and then you do a cross product here. Okay, now that cross product, in a determinant sense, is the product of these two minus the product of those two. The down diagonals are plus, the up diagonal is minus. Okay, so it's U2, V3 minus V2, U3. That doesn't matter which order you say that. That's times the I. Now, here's the squirrely part. And this is the cofactor expansion. If you have add determinants, just bear with me here. The signage that you do here, for any square vector, or square matrix that you have, and to do determinants you have to, assign a sign to each position. And here's how you do it. Start at upper left, that's always positive. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Or a plus, minus, plus, minus, plus, minus, plus, minus, plus. As long as you're going right, left, up, or down, doesn't matter how you do it, it assigns pluses to these and those, and minuses to these and those. Okay? So, since you're doing J next, the sign of that J vector, the J element here is going to be negative. That's why the minus sign is there. Now this is the hard way to do it because you have to remember that. But again, you wipe out row and column for that J, and then you do your determinant. U1, V3, because that's your down diagonal, minus V1, U3, that's the up diagonal. But remember you have the minus sign in front. Then to do the K, that is in position, positive position, plus, minus, plus. Okay? So it's going to be a plus here, wipe out the row and column, and then do your determinant here, U1, V2, minus V1, U2. And that's times K. This is the component there. And then when you write this out, I'm sorry. I did it here. So this is U2, V3, minus U3, V2. I prefer to do V2, U3. It doesn't matter what order you multiply. Make sure you got the minus sign here. Always positive down diagonal, negative up diagonal. Positive down diagonal, negative up diagonal. Remembering this is a positive position, negative position, positive position. That gives you your answer. So that's somewhat better than memorizing this, right? So many places to get your signs wrong. Now, okay, let's continue here. Notice that the minus sign in front of the J component, just notice that. Each of the 2x2 determinants can be evaluated using the diagonal pattern. The down diagonal is plus, the product of the down diagonal is plus, the product of the up diagonal is negative. Okay? They always put BC, I would put C to B. Doesn't matter. So here's just do one. Do this one. What's the determinant of that? Two, 4, 3, negative 1.
Negative 2 minus 12.
Which is?
Negative
14. Bingo. Or yeah, you can't say bingo now. Okay, what's this one?
12 minus 0.
Which is 12. Perfect. Okay? Any questions on simple determinants? Okay. Now, here are two vectors. U, I minus 2j plus k, v, 3i plus j minus 2k. All right, if I show you the easier way. To me, it's the easier way. Now, again, this only works for threes. Yes? 1 minute to go. Okay, let's see if I can get it done. Y'all may have hit this before already. U cross V. What we're going to do here, you want to just wait till next time?
Yeah, that's what we should do.
Okay. So we'll start next time with example 1, and I'll show you the easier way to do it. 3 by 3s. Okay, let me get this in place. And let's see, we probably didn't. Oh, yes, you can do 3 or 5. I think you can do those without any problem whatsoever. Okay? I hope you can. If not, we'll do those next time too. We'll wait on the rest of them. And those are both found at Calc Chat, so if you can't figure out how to do them, look at Calc Chat. They're pretty easy to do. Okay? All right, and we'll pick up next time. What's that? I can't hear you. What'd you say?
No.
Oh, okay.
I won't be here tomorrow.
Okay, promise or threat? Okay, never mind, I'm sorry. Okay, yeah, you're going to D.C. or?
No, I got something with work.
Oh, I see, okay. I was going to say, because I had a student this morning said he wouldn't be here Wednesday because he was going to D.C., but I thought maybe you were in STEM also, but you're not. Okay. All right. Then somebody in STEM is with Dr. Thomas. Huh?
Wayman Holloway is taking us to Atlanta. I need to go to DC. Our meeting's in Atlanta. What? This sucks. Nah, actually, I don't go to DC. I heard they're going to DC and then leaving and then coming back the same day.
I don't know. They may be. I wouldn't be surprised.
That is horrible.
Huh?
That is horrible.
Yeah.
Most of your day is going to be on an airplane.
Yeah. And I don't sleep that well on airplanes anymore, so.